Welcome back. We're going to start a new chapter today. So, and we're going to be jumping ahead in the book. So this is now chapter 45, unique factorization domains. And so let me set the stage by just reminding you, there's the fundamental theorem of arithmetic. So the fundamental theorem of arithmetic. And remember, I kind of mentioned this last time, but I want to state it precisely now. So the fundamental theorem of arithmetic says if we take an integer, let's say n in z, where it's greater than or equal to 2, so with, let's say it this way, n greater than 1, then there exist primes say p1 up through p sub k, and some exponents, some natural numbers. So let's say, I'm going to use alpha, I think. Yeah, alpha 1 up through alpha k in n, such that n is equal to p1 to the alpha 1 dot 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 p sub k to the alpha k. N can be expressed as a product of primes. And what we do is we collect, they don't have to be distinct, and so you collect the p1s all together and raise them to the alpha 1. You know, the p2s, the 3, and so on. Now we know that we proved a similar result for polynomials, right? So, and by the way, we have not proved the fundamental theorem of arithmetic yet. We're going to prove this. In fact, we're going to prove it a little bit more generally. And you can extend this. So notice here, we only consider integers greater than 1, but you can actually extend the fundamental theorem of arithmetic to all numbers that are not 0 or plus or minus 1. So we got to get rid of 0, and then we get rid of the units. So anyways, we will return and actually prove this. We proved a similar result. And that's really what I want to do, is just sort of give the analogy, right? There is the fundamental theorem of arithmetic, and then we proved a similar result for f bracket x, right? So if f of x in f bracket x is non-constant, then we can factor it. So then f of x is equal to the product p1 of x dot 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 p sub k of x, where each pi, so pi of x, is irreducible. So in this case, then, irreducibles play the role of primes, and so moreover, this factorization is unique I don't know how that says unique. Is unique up to ordering and multiplication by units. So let's say and units. All right, and you can look back at the last lecture. That gives the precise statement of this. Okay. So a couple of things to point out here. Now, this first thing is not obvious. So it turns out the key to the proof of this theorem right here, the one that we proved last time, the key of the proof is the fact that f bracket x is a principal ideal domain. Now, I mean, I really didn't mention this fact as we went through, right? But we'll see once we start generalizing things, and I'll come back and mention, oh, by the way, remember I mentioned this PID fact? It turns out that, right, that this whole thing relied on the fact that P of X is a principal ideal domain. And let me just say, so how did it work? How did that proof go? Well, we just took a polynomial and we said if it's irreducible, fine, stop, we're done. Otherwise, split it as a product, right? Two polynomials. If those are both irreducible, done. Otherwise, split those as products. And the point was that that splitting process, right? You can iterate that process, eventually stops, right? The fact that the process terminates actually relies on the fact that f bracket x is a principal ideal domain. And then it turns out, right? So we have so what we've seen is that in Z there's a unique factorization statement. For f bracket x there is a unique factorization statement, and it turns out so we will see there exist rings where unique factorization does not hold, right? So we've stated, or we've shown that in Z, when you factor polynomial or integers as a product of primes, there's essentially one way to do it, up to ordering. When you factor polynomials, there's essentially one way to do it, up to ordering plus sliding units around. And it turns out that there are places where you can have a certain object, a certain element of the ring, where it factors in two completely different ways, right? So we get non-distinct, non-unique factorization. So we'll work up to that. So now a few definitions. So let's let R be a commutative ring with one. And then I need a couple of elements, so let's say little a and little b in capital R. Two parts of this. So A divides B if, right, so we've defined divides in the integer setting, in the polynomial setting. Now we're going to define it in general in a commutative ring with one. So A divides B if there exists some C in R such that B is equal to A times C. And the notation is the usual thing, right? We write A vertical slash B. So there's part A of the definition. So part B, A and B are associates. If A is equal to B times U for some unit U in capital R. Notice if you can express A equals B times U, then you can also write it as AU, or A times some other unit equals B. So let's just say exercise. Part B induces an equivalence relation on capital R. Or you can say little a is equivalent to b if and only if a is an associate of b. Right? It turns out that's reflexive, symmetric, and transitive. Right? It's easy to show. Okay, another definition. So in this case, so let's let D be an integral domain, and I need some P in D where P is not 0 and P is not a unit. Two parts of this definition. I guess I can put them here. So P is an irreducible of D if whenever P is equal to A times B for some A and B in D, either P is, not P, A is a unit, or B is a unit. So this definition matches the definition that we did when we were talking about polynomials, or when we defined irreducibility of polynomials. And then part B, so part B, P is prime if whenever P divides A times B, we have P divides A or P divides B. Okay, so there's some terminology. And some observations. We need some observations here. So let's see. Yeah, in fact, we have a few observations to get, or we get from these definitions. So observations. Okay, the first one, so suppose P is an irreducible and Q is an associate of P, right? So P is equal to Q times some unit or vice versa. So then we have Q is equal to U times P for some unit U in our integral domain D. Now, suppose that the Q factored. So if Q is equal to A times B, then P is equal to, let's say, U inverse A times B. I just substituted, right? Bring the unit over, and then we have that, and then put some parentheses in there. So P is equal to that. So what does that tell us? So U inverse A is a unit, or B is a unit. In the case that U inverse A is a unit, it's easy to see then that A is a unit. Follows. that A is a unit. And so as a conclusion, right, so what do we have? B is a unit or A is a unit whenever Q can factor as A times B. So conclusion, Q is an irreducible. So if you want to paraphrase this, I mean, what are we saying here? So what we're saying is that an associate of an irreducible is an irreducible. So there's our first observation. The second observation in Z, a prime number is usually defined as in A, and then part B is known as Euclid's lemma. So in a way, things seem backwards here, right? We defined irreducibility, but you know what? If we were talking about the integers, if D was Z, then this would be, we would say this means that it's prime, right? That's what, and then this would be this sort of consequence of being prime. And so instead, we've got irreducibility fitting the definition of what we normally think of as prime, and then prime is actually this consequence of being prime in the, right, this is Euclid's lemma. And then one more observation, so 3. If P is prime, and in our definition as defined over here, and P equals AB for some A and B in D, then P divides A or P divides B, right? If P is equal to AB, then of course P divides A times B, which means by virtue of being prime that P has to divide A or P has to divide B. So if P divides A, then A is equal to P times, I'm using here C. And so P is equal to PCB. And then by cancellation, one is equal to C times B. So what does that tell us then? It tells us that B is a unit. So I'm going to say, and so and then similarly, if P divides B, we would conclude that A is a unit. So similarly, if P divides B, then A is a unit. So what did we just prove? We proved that if P is prime, then P is an irreducible. So, let's say, so therefore, P is an irreducible. So if you want to sort of paraphrase this, what we have is a prime implies irreducibility, or irreducible. And so this is sort of backwards again, right? In the integers, we define primeness like this, and then we prove Euclid's lemma as a consequence. It turns out that it actually goes the opposite, that somehow being prime is stronger, at least at first glance. P is stronger than being irreducible. So this leads to our sort of most important definition of this chapter. So an integral domain say capital D is a unique factorization domain, which we will typically abbreviate as UFD if so two parts of this. Let me put the parts over here. Yeah, so part one, let's put part one here. So every non-zero non-unit of D can be expressed as a product of irreducible. So there's the existence portion, and then we need the uniqueness portion. The second part, if what do I call it here? I'll say A. So if little a is in D, and A can be expressed in two different ways, say P1 up through PK, and also equal to Q1 up through QM, where each Pi and Qi in D is irreducible, then K equals M and up to reordering Pi and Qi are associates for each 1 less than or equal to I less than or equal to K. Let's end just with a couple of examples here. There's a lot of terminology that we had to get built up. So first example, Z is a UFD. We don't know this yet, right? We know, we've heard the fundamental theorem of arithmetic, but so this is still to be proved. F bracket X is a UFD, and this is what theorem is that? Well, we proved this. What is it? 27. I can't remember. Is it 2714 or 2712? Yeah. Oh, right. It's 2714. Right. 2714. Yeah. Okay. Okay, that's a lot of terminology. I'm going to stop here because now we're going to have to pick up with sort of some more high-powered stuff. So, okay, I will see you next time.